it would actually give up an electron if it's put in the presence nearby to an actual chlorine molecule. So the sodium gives up an electron, becomes positive, chlorine gains an electron, becomes negative, and those completely opposite charged or oppositely charged particles are attracted together by EMF, electromagnetic force. Okay? And then we talked about how covalently bonded structures, let's say water for example, because it's really common, we share electrons. And that sharing of electrons actually creates an electromagnetic force, where these electrons are held in a region, we call that a sigma bond, this region, a region of space created by the positive charges of the nuclei here. So there's a kind of a boundary line holding those electrons in place. Those electrons are also attracted to this nucleus and to this nucleus. So these electrons are actually what is holding together with electromagnetic force, or actually all of it together, all the nuclei, all the protons in the nucleus, and the electrons, are what's holding this whole structure together. Okay, but that's the whole molecule here. All right. But now we've also talked about in a previous unit, Unit 4, that when we put this molecule together and we figure out its three-dimensional structure, we end up with a bent shape, and we've got a couple of lone pair electrons sticking up here on one end. Okay, and that oxygen has more electronegativity, which means it is pulling on the electrons in the bonds, the electrons it shares between the oxygen and the hydrogen. And it's pulling on them more strongly than hydrogen pulls back. So overall, the electrons spend more time where the oxygen is. Okay? Overall. Okay? It's kind of like you and your friends. All right? I bet you got a friend who has more toys than you do, or better toys than you do. Okay? Or maybe you got better toys than they do. Well, where do kids spend more of their time? Where the toys are, right? All right? So the electrons are going to spend more time over here with the oxygens because it's got better toys. You got me? You got me?
Wait, why does it have better toys?
Oh, why does it have better toys? It's richer. You got more money. The guy's I don't know, an engineer or something, you know, and your family's, you know, you got a car mechanic or something. I don't know. I don't know. Okay, I'm just saying. I mean, I do know, but it's just too. It's way beyond the scope of this class here. I don't want to get too.
Electrons stay with the oxygen instead of the hydrogen.
We would have to go back into structure and go back to shielding effect and all the things that make up the structure of an atom and get even deeper into it than we did in Unit 2 to really understand that. Okay. I really don't want to take the time to get away from what we're trying to talk about here. Okay? Just take it's a great question. I'd love to talk to you about it outside of class. But right now, let's stick with what it is that's happening here in terms of what's going to make this a polar bond, because the electrons are spending more time over here because they got better toys, right? All right. So the electrons are spending more time over here. On average, the electrons are here more. The electrons are negatively charged. So this part of the molecule where the oxygen is, that's more negative overall because the electrons are spending more time there. There's an even number of protons and electrons in the whole molecule. But overall, they spend more time here. Okay? So just like whatever house it is that has the better toys, there's a greater density of kids there. There's a greater density of electrons here, making that part of the molecule more negative. Therefore, we've talked about this before, the bent molecule that is water is partially positive out here where the hydrogens are located and partially negative here where the oxygen is located. Okay?
What is that?
That's a partial, that's a Greek letter, which we just use for the symbol for partial positive when we put the positive sign next to it. Okay? And so, another way we drew that, we said that we did it like this to show that this whole idea about the electron spending more time there. Okay? So this is the partially negative part. This is the partially positive part out here. Okay? And so what we're creating here then, through this process of electronegativity difference, is a polar molecule, because this part of the molecule is more negative. So this ionic compound, where I've got more sodiums and more chlorines, and they're arranging themselves in this nice crystalline structure, they're held together by opposite charges. Metals, like iron, which has a couple of electrons on the outside that are a little more loosely held. So those electrons on the outside that are more loosely held then become a kind of sea of electrons, a kind of a glue because they're flowing around here, but always enough electrons around that iron to still make it an atom, but just loosely held, but still flowing. This Electron See Model is what makes the one metal atom stick to another in a pure metal structure. Okay? But now we've got a situation, we've got a discrete, separate building block here called the molecule. The molecule doesn't split up. The molecule stays together, but one molecule will stick to the next. Okay? Because of that partial charge now. This is a complete charge. This is a complete charge difference. This is a partial charge between one water molecule and the next. Okay, one water molecule and the next is attracted, one water molecule is attracted to the next water molecule because there's a partial charge difference on one end compared to the other. So the oxygen is attracted to the hydrogen end because the hydrogen end is where the partially positive end is located, and the oxygen is where the partially negative end is located. But this is not so strong as this is or this is. Does that make sense? Because these are completely opposite charges, and this is a partial difference in charge. That makes sense? Okay, let's throw in another idea. We've talked about this before too, and we're building up here. You can think about this as making a ball of string. Okay? You start out with a ball of string being really small, and you wrap more and more string around, and it gets bigger and bigger and bigger, right? Well, our understanding of chemistry gets bigger and bigger and bigger as we tie more and more of these pieces of string together to make up the bigger idea of what makes up all of chemistry. Okay? And that's what we're getting to. We're tying all this stuff together. We started out in Unit 2 talking about the structure of the atom. Then after we understand the structure of the atom, we talked about how the electrons move around and how we create these polar molecules. That was Unit 4. Now we're in Unit 7. We're talking about how these individual molecules are attracted together by all that polar stuff. Okay? And we talked about ionic stuff in Unit 2, and then went on to Unit 3 to talk more about it too, and moving the electrons around to make those, ionic structures. Okay, now we're talking about how we make it into stuff big enough to touch, okay, to manipulate, to use. It's here in the air as well. Okay, all this stuff is affecting all these particle interactions that we can actually experience. This is the stuff we can actually observe. All this other stuff is circumstantial stuff we can't see, we have evidence of, but we have to assume it's there based on the weight of the evidence. Okay? Now we've got stuff we can actually see. We're getting to stuff we can see because of the attraction of these particles. Okay? Now, so this stuff in the video, anyone remember what the temperature of this stuff when it melted? What was the temperature? 801 degrees C. Wow, you were listening good. Good for you. Okay? But I bet you already know what temperature this melts at. What temperature does this melt at?
100 degrees Celsius.
No, that's when it boils. 100 degrees Celsius when it boils. It melts at 0 degrees C. 0 degrees C melting point, 100 degrees melting point, 1200 degrees melting point. Okay? Why is this one so much lower than that one?
Because that one's water. Yeah.
Partially bonded.
Weaker attraction is the key. The polar attractions, well, this is very polar. And as far as polar attractions go, there's a very strong attraction between these water molecules. But it's nowhere near the attraction that's between the iron and the Electron See, or the sodium ion and the chlorine ion. And the result is much higher boiling point, much lower boiling point. Or for that matter, much higher melting point, much lower melting point. Much lower freezing point, much higher freezing point. Okay? So freezing and melting happen at the same temperature. Freezing and melting happen at the same temperature. One just going in one way and one's going the other. Okay? As you add heat to water, or let's put it this way, as you add heat to ice, the temperature rises to the point of temperature where it starts to melt. It starts to melt at 0 degrees C. On the other hand, you take heat out. Okay, we have water at, say, 10 degrees C. We take heat out, the temperature goes down until it starts to freeze. And it starts to freeze at 0 degrees C. Okay? So freezing temperatures and boiling temperatures, freezing temperatures and melting temperatures are the same temperature. Boiling temperatures and condensation temperatures are the same temperature. Boiling means you turn it from a liquid into a gas. Condensation means you turn it into a gas, from a gas into a liquid. You condense it. Okay? All right. Back to our overall idea now about structure and how structure affects these physical states of solid, liquid, and gas, and so forth. Really strong attraction between individual particles, really high melting point, really high boiling point. Really strong attraction between particles, opposite charges here. The C of electron theory is what it's called, or the Electron See Model is what it's called. Opposite charges, really high boiling point, really high melting point. Okay? Polar attractions. The molecules don't break down. The attractions between the molecules break down. Now you got to know this. This is where students get tripped up. They don't understand the difference between breaking down the bonds between the atoms in the molecule and breaking apart the molecules. So let's make this clear as we can. When water melts, the molecules separate. The molecules do not break apart into separate hydrogen and oxygen atoms. When water melts, we're just taking the water molecule and separating it from this one. And really, we're not truly separating it. I'll get to that in a minute. Okay, but they don't stick together in a rigid arrangement anymore.
We're just like loosening them.
Well, it's kind of like loosening. It breaks it apart, sort of, but no, I'll talk about that in a second. Hold on. Just hold on with me, okay? But the strength of attraction between partially negative, partially positive ends on a polar molecule are not as strong as you would imagine as a fully charged separate set of charges in ionic or the Electron See model for metals. That makes sense? But the molecules don't break down. When I melt water, I only separate the water molecules from each other. I don't separate the hydrogen and oxygens from each other. And when I boil water, I just get the water molecules to break out away from each other. I don't get the oxygen and hydrogen to break apart, just the molecules to separate. Yes?
Is there a way you can get something hot enough for it to turn it like straight from ice into gas? No, it's sublimation.
It is called sublimation, you're right. So the question is there a way to get water to go straight from being a solid to a gas and never go through the liquid state? The answer is yes. And it happens in space. Okay? There is no liquid water in space. The only reason that water can be a liquid is because there's enough air pressure to make it be so. Okay? So they talk about the Earth being in the Goldilocks zone of our solar system. Okay? It's in the Goldilocks zone because it exists in a region where the temperature is just right, and it just happens also, we also have this layer of air on our planet's surface, so we're not cold enough to condense that air into a liquid. So we've got this gaseous air. Okay, we've got this gaseous surface on over our planet, outer planet, creates pressure along the surface, pressure enough to make water be a liquid, the Goldilocks zone. Okay, if it were further out, just a little bit further out from the sun, wouldn't happen. We'd be Mars, dead planet. A little bit closer to the sun, it'd be Venus, wouldn't happen. Okay, so we're in the Goldilocks zone for liquid water, and guess what also can't happen without liquid water?
Life.
You and me, life. That's exactly right. Now, back to this. So this is important, all right? But the answer to the question is, yes, you can get water to go straight from being a solid to a gas if the pressure of the air around it is low enough. Okay? Right, CO2 is a good example also. You can buy solid CO2 in the grocery store called dry ice, but it never becomes a liquid. I put dry ice on this countertop, and we've used it in labs in here before. It never becomes a liquid. It doesn't melt all over the lab table. It goes straight to being a gas. Okay? That's called sublimation. That's the term you used a moment ago. Okay? But CO2 can be a liquid. There's just not enough pressure in this room to make it a liquid. We have to put it under a lot more pressure. So you see a lot of trucks going down the road with liquid CO2. Okay? Usually I don't know, the ones I've seen right here are painted green. But it'll say liquid CO2 on the side, on the little diamond-shaped placard on the side. I don't know. I don't know what you use it for. But anyway. I don't know. Grow plants. Liquid CO2 to grow plants? Okay, I'll take your word for it. He says you grow vegetable plants. I don't know how you grow vegetable plants with liquid CO2, but nevertheless. But I'll tell you this. Okay, this is cool. All right, you guys were talking about this earlier. That we have our first chemistry club meeting this week. I sent you an email notice about that. We're going to be doing tie dyeing. If you want to tie dye, you've got to first prepare the garment. Okay, the cloth has to be prepared. The email tells you how to do that. All right, or you can bring it in here and I'll put it in a container to prepare it. All right, but the reason this has nothing to do with that. What I'm getting to is other people have said, can we just please blow stuff up? All right. So, as far as blowing stuff up, the difference between a liquid and a solid and a gas in terms of the space it takes up is huge. Most explosions, in fact all explosions, are rapidly turning solids or liquids into gases because gases take up way more space, hence an explosion. Okay? Now, how does this apply to this? Well, if we turn this from a liquid into a gas, we get the molecules completely separated apart. But let's don't go too far yet because I want to go back to liquids. The difference between the solid form of water, we call ice, and the liquid form is not that they separate so much, but really that they simply stop from being completely locked together. See my fists here? Do this with me. This is what a solid does. Solid molecules are just stuck together. They're twisting and turning, all right? Like some second grade kid that can't sit still with ADD. Okay, they're twisting and turning, all right? But they're there in place. They haven't moved. But now when they become a liquid, they do this. This is a mosh pit. Y'all know what a mosh pit is?
Yes.
Okay, mosh pit. Huh? Yeah, no, that's a mud pit. Anyway, now, what's the difference between this then and a gas?
A gas is like this. Okay.
All right, do it with me. Come on, guys. You got to get with this program here. We're trying. Yeah, you got that. So, solid, twisting, locking in place. Okay, liquid, and gas, all apart. Okay. All right. All of us in here look like Rocky on the steps of that place. When his hands all out like that. All right. You don't have the. Oh, he's got the hoodie on there. Okay. All right. So if you have no idea what I'm talking about, you need to go back and watch Rocky 1. So, what's the name of that song they play when he's on the top of those steps? Yeah. Anyway. All right. So, we can explode water. How would we explode water? Really sudden. We'd have to have a really, really sudden change, but we could. Okay. Huh? We could explode water if we could get it to turn into a gas fast enough. But most of the time, what you do with the explosion is you get a rapid chemical change from liquid to a gaseous state, or from solid to a gaseous state. Okay, not a physical change, but a physical change can cause an explosion. It can happen. All right. Now, so this is the way that we get these particles stick together by the opposite charges. So really high melting and boiling points. Okay, these are stuck together by opposite charges, really high melting and boiling points. Sort of not so high melting and boiling points anymore. Okay, got a polar molecule, opposite charges, but still within the same structure. So the opposite charges aren't separate things. The opposite charges exist within the same structure. So there's some stickiness between those molecules. They get them to stick together, and it's not so hard to get them to stick together, not so hard to separate them, but these are really hard to separate apart. So it's a really high boiling point and melting point. Got it? All right. Now, what about a molecule? And we've played with this stuff. How about we use N2, nitrogen, and that's just one nitrogen bonded to a second nitrogen. Okay? All right. Does this have, what is the electronegativity difference between one nitrogen atom and another nitrogen atom? Trick question. Really simple. What? Zero difference. So without any electronegativity difference, can we have a polar molecule? No. The only reason that this is a polar molecule is because of the extreme electronegativity difference between hydrogen and oxygen. Okay? No electronegativity difference, no polarity. No electrons spending more of their time one place than another. All the electrons spend the same amount of time everywhere. Okay? But let's think about this a minute, okay? Here's our electron cloud around this nitrogen molecule. All right? The electrons are in that electron cloud. They're moving chaotically, meaning you can't really predict what direction they're going in. They're moving in all kinds of directions. They move in a straight line until something makes them change. But over the course of time, they don't go in the same all together in the straight line. Okay, not like electricity. Okay, they're moving around here more or less chaotically. Okay, randomly. All right, so they're moving randomly. And think about this like playing musical chairs. How many of you played musical chairs before? Okay, a lot of hands going up. Maybe about half of this room. Well, there's some more hands creeping up now. Okay, everybody's played musical chairs. All right. So when the music stops, everybody jumps in the chairs, right? Well, instead of the music stops and everybody jumps in the chairs, we're going to play sort of a freeze thing, okay? Where we're going to, all the electrons moving around randomly, and suddenly the music stops and they freeze. They don't move anymore. They stop in place, which can't happen. But we're going to say that, okay? So they're going to stop. Where would the electrons be?
Anywhere.
Anywhere. Okay? Are they going to be equally spaced all the way around?
No.
Could they be equally spaced all the way around?
Yes.
Yeah. But they might not be equally spaced. They might all be grouped in here somewhere, and only a few over here. Because statistically, if they're moving pretty much chaotically, that's what's happening. Okay? There's going to be occasions when they're equally spaced, but more often than not, they're going to be kind of grouped up, sort of, kind of, and sometimes grouped up a lot. What charge does an electron have? Negative. What charge does the proton have? Positive. This is now a polar molecule. But it's only for a tiny little instant in time. Tiny, tiny, tiny fraction of a second does this happen. Because those electrons don't really freeze. We're theoretically talking about freezing them so we can imagine what's happening, but they don't really ever stop, do they? But for a very, very tiny fraction of a second, I got a polar molecule here. Now overall, most of the time, it's not polar, but some of the time it is. And most of the time it is, actually, but the amount of polarity isn't significant except for a smaller fraction of time. And the smaller the molecule, the smaller the fraction of time. That makes sense? Mm-hmm. All right, now, if I've got a polar molecule, I've got a way to make them stick together. If I've got a polar molecule, I've got a way to make them stick together, don't I? Because now this is partially negative up here, and it's partially positive down here. And so this molecule will stick to the next one. And we've used liquid nitrogen in here. You've seen the result. And how did we get them to stick together? What was it that allowed us to stick them together? Because there's nitrogen in the air. Most of the air is nitrogen, right? How did we get liquid nitrogen? How did we get to be a liquid and stick those particles together like this? Huh? Well, we could increase the pressure and get to be liquid, right? But was the pressure any higher in here than it is on any other day? No. But that's how they got it to be there. What they did was they put the nitrogen under high pressure, and it created a lot of heat. Because what happens when you increase the pressure? We get gas laws in this unit. What happens when you increase the pressure on something?
Temperature rises.
Temperature also rises. That's Gay-Lussac's law, which said you don't have to know it, but you should know the relationship between pressure and temperature because we talked about the combined gas law. All right? So we increase the pressure. In fact, we actually decrease the volume. The main factor is increasing the pressure. We allow the temperature to equilibrate, all right, and we get a liquid. Then when we release that pressure, the temperature goes down, and when temperature goes down, we still get it to be a liquid because we're slowing the molecules down. Yes, yeah. So that's the way they get it to be a liquid. All right, but we got it at really, really cold temperatures, which is what keeps it a liquid. But in the room I showed you an example, it was boiling, wasn't it? Okay, because the temperature in here was high enough that liquid was actually boiling in here, even though it was really, really, really cold. Now, we slow the molecules down. Here's what's happening. If the molecules are moving really, really slow, and you have just a tiny amount of polarity due to the shift in, this is called a shift in electron density. That's a term you probably ought to know. Shift in electron density or uneven electron density. So polar molecules have uneven electron density that's permanent. Nonpolar molecules have temporary electron density differences that are temporary. Okay? Nonpolar molecules have temporary electron density differences. Polar molecules have permanent electron density differences or shifts in electron density. Okay? All right.
One more time, what
Polar molecules have a permanent difference in electron density. That's what makes it polar, because the electrons are more grouped up in one place than another. Nonpolar molecules have temporary electron density differences within an electron cloud. Okay? And that's what makes it temporarily polar. Now in the video they call that a van der Waals force that causes this molecule to be attracted to another. I really think that van der Waals refers to a slightly different thing that is very, very similar, but I'd prefer you to know the term London forces. Capital London, not named for the city in Kentucky. Yes, there's a London, Kentucky. But I know you're thinking, yeah, I know. But we're not, I know you're all thinking about London, England, but you know, there's a London, Kentucky. Anyway, it's called the London forces, named for a person, not for a city. Okay? So it's London forces that are holding this nonpolar molecule to the next. Okay? Now, we could call it a van der Waals force because it's very closely aligned, same concept, but for us, I'd rather you call it a London force. Okay? London. But this is very, very temporary. All right. Very, 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 very temporary. That's something we're going to say. They don't say very. They don't even hardly pronounce the R. Very. That's their very, right? No. All right. I don't want to see y'all, I want to see you. Okay. Of these four substances, now I'm not talking about individual particles here. I'm talking about lots and lots of particles, okay, grouped together. So we're talking about the interaction between the particles. All right. What kind of interaction do I have between the particles here in this formula? Ionic, because it's a metal and a non-metal, right? Okay, that's ionic attraction between particles. The structural particles for this would be ions, oppositely charged stuff, right? What kind of interaction do I have between the structural particles here? Well, that's within the molecule. But the molecule makes up a structural particle. So what kind of interaction is there between one molecule and the next? Atomic? Ionic? Well, it's all EMF, all electromagnetic force. Is this a polar molecule or non-polar molecule? Polar molecule. So what kind of interaction do you have between this particle? This has actually three separate particles that are structural particles because it's ionic. This is an ion. You got two ions here. Okay, ionic attraction. The structural particles here are individual, separate monoatomic ions in this particular case. But this makes up the whole thing is a structural particle. Okay? The molecules are the structural particle for molecular substances. The molecules are the structural particle for molecular substances. So let's see. You got ions, that's a structural particle. You got atoms, that's a structural particle in certain types of things. And somewhere in between those two, we got metals, okay, which we're going to call an atom because the electrons are all there, even though they all have some behaviors that are like ions. Now we got a third particle that makes up structure, molecules. Make it? Or actually four if you say atoms, ions, metals here, and molecules being structural particles, okay? So four different types of particles, even though we only have three names, because we don't have a name for the one that's in metals. We call it an atom, even though it has some behaviors kind of like ions. You with me? Got it? All right. This is a polar molecule. How do we know it's polar?
Because it's a permanent shift.
Permanent shift. Electronegativity difference between the bonds is that polar range greater than 0.5, right?
Yes.
And you're talking about the way the molecule's shaped, right?
Yeah.
Okay, she couldn't think of the name of it. This has a trigonal pyramidal molecular shape. Okay, so it's an uneven arrangement of bonds or uneven arrangement of electronegativity making a polar molecule. So the molecule is the structural particle. It has a partially positive and partially negative end. So it has an attraction from one molecule to the next that's permanent because of a complete shift or permanent shift in electron density. How about this molecule right here? Is there any difference in electronegativity between oxygen and oxygen?
No.
No. So this is a molecule. Is it polar or nonpolar? Nonpolar, because there's no difference in electron density, right? Right? Not permanently anyway. So the only kind of attraction between an oxygen molecule and the next one is this temporary shift called the London force, or resulting from a London. The shift in electron density causes a London force because it causes a temporary polarity. Okay? All right, let me go through that again. This is a nonpolar molecule because there's no difference in electronegativity. Okay? But it has a temporary polarity when the electrons are unevenly arranged. We have a shift in electron density, creating a difference in electron density, creating a temporary polarity, and that temporary polarity, because it causes a partially positive and partially negative end, gives us a force of attraction between one of these molecules and the next. Got it?
Yes.
All right. Now, what about this one? What is the structural attraction with this? Huh? It is atoms, the structural particle, but the attraction is called what? It's kind of an electron See. It's almost ionic because it's like the positive part of the atom that, when we don't consider the part that has loosely held electrons, the electrons being freely flowing, but that freely flowing electrons creates a kind of a ionic glue, even without a negative ion. We have negative electrons. Okay. All right. So theoretically, that's something entirely new for you. I don't think you probably ever heard this before. Doesn't sound like it. Okay. So the Electron See model is a whole new idea, but it's not so much divorced from the idea of ionic compounds being attracted by opposite charges. All right? All right. But the attraction of nonpolar molecules or polar molecules, that's a little bit new. We talked about polar molecules having attraction to each other earlier in this semester, but we certainly have never talked about this temporary polarity like this. Okay, so that's completely new. All right? All right. Now, knowing all that, of these four right here, which one is going to have the lowest melting temperature? Which one's going to have the lowest melting? That had the highest melting temperature because those particles are held together really strongly. Huh?
Not oxygen.
Well, just oxygen.
Oxygen.
No, oxide would have a negative charge. Oxygen. So that has the lowest melting temperature. Okay? Which one is in the middle?
Nitrogen hydroxide.
What is that called? Come on, guys. I told you you had to memorize that. Ammonia. Yeah. IUPAC rules say we call this nitrogen triiodide, but we don't call it that. We call it ammonia. Okay? All right. Then these two will have really high boiling melting temperatures, and it's kind of hard to tell which one is going to be higher because metals and ionic compounds have kind of the same high melting boiling point temperature range, even though overall, if you average everything out, metals tend to have a higher melting boiling temperature than ionic compounds do. Okay? Now, the only thing we really haven't talked about are like diamonds. We talked about it, but only structurally, right?
Diamonds?
Yeah, diamonds. We talked about it in here today,
Yeah.
didn't we? All right. Because diamonds are an unknown number, potentially infinite number of carbon atoms bonded in a three-dimensional lattice structure, but they're bonded covalently. The covalent bond itself may be weaker than the ionic bond, but the combined effect of all those covalent bonds makes the overall structure even stronger than those of ionic compounds. Okay? We might symbolize this like this because we don't know how many carbon atoms it is. So that could either represent diamonds or it could represent graphite. Okay? So these lattice structure covalently bonded things have an even higher average melting temperature than do ionic or metals, ionic compounds or metals. Okay?
Does that say CX?
Yeah, C subscript X.
Because it doesn't matter what it is.
We don't know how many unknown number.
That's what I said.
I mean, we could also write it, I suppose, theoretically speaking, like this. But, you know, because it is a whole number.
Yeah.
But traditionally it's CX, okay?
Okay.
All right. So we can actually make a prediction about whether one thing might melt before another based on this idea. Now, going back to what they said in the video about amorphous solids. So amorphous solids don't have a structure that's where you can find a set of atoms bonded together in a structure, and the next set is just exactly like that. The next set is just like that, and that would create a crystal. Okay, ionic compounds do that. Diamonds do that. That's a covalent structure. But there are also amorphous solids, and probably the classic example of that would be glass. Okay, glass is an amorphous solid, and it could be a crystal if you allow it to cool slowly enough. But there's only one place where that happens, and we talked about that, and that's in a volcano, where it cools slowly enough where it can be an actual, truly glass crystal. Okay? Most amorphous solids don't have a melting temperature you can actually put your finger on. It's a range of melting temperatures. Okay? Amorphous solids have a range of melting temperatures. So, the plastic seat you're sitting in right now is an amorphous solid. If I were to melt it, it wouldn't melt at one temperature. It would melt at a whole range of temperatures. It'd start melting at one temperature and would finish melting at a different temperature. Whereas water melts at only one temperature, 0 degrees C. Okay? The desktop, which is made partly out of wood, partly out of plastic, if I put it in an environment where I don't have any oxygen, I can melt it, and it would melt at a range of temperatures because it's an amorphous solid. Yep. Yeah. I could melt your clothes, even if it was made of cotton, if I got the conditions just right. Okay? All that can happen but it's an amorphous solid. And your hair. I can melt your hair. I can melt your skin. But all amorphous solids, so it would melt at a range of temperatures. Okay? You with me? Now, let's talk about homework. That handout I gave you, which is about 7, 8 pages there, make sure you study that tonight. Read the whole thing. Okay? I want you to come in here tomorrow knowing enough about it to be able to ask intelligent questions and have an intelligent discussion. Basically what this handout does is give you even more detail about all the stuff we talked about today. Okay? But it's a really good way to review the theory. Listen, guys. Please be quiet. Sit still. Pay attention. So we've been talking all about theory today. Okay? We've done all the math already. This is the theory part. The theory means you've got to be able to imagine what's happening with those particles and run that movie in your head. Okay? And use it in a practical manner. All right? This is going to help you reinforce that idea. If all you do is listen in class, you're probably not going to pass the test. So you've got to put some more effort into understanding it on your own, and that's what studying this handout's about.